Okay, so a very good morning to all. Okay, so myself Javed, and this PPT is been taken from Professor P. Nagbhushan. Okay, okay. So these are some of the textbooks. Okay, these are some of the textbooks. Just a minute. Let me manage my screen. Okay. Okay, so these are some of the references. Okay, the best book which I had already suggested to you in the introduction to programming course was that How to Solve It by Computer by R.G. Drome, and this is the book which you have to, which will also be useful in this particular course. And then the other book, which is Analysis of Algorithms and Active Learning Approach, which is Jeffrey J. McConnell, and then you have Design and Analysis of Algorithms, right, by Ananya Levitin, and then you have Computer Algorithms by Horowitz Sahni, okay, Rajshekharan. This is another book. Introduction to Algorithms by T.H. Corman, okay, Lizerson and Reveset. Okay, so this is the book, the fifth one, Introduction to Algorithms. You please try to read this book for this particular course. Okay, a Corman book, I would suggest you that you try to purchase it or have it the online version, which may be available freely over the internet. You can just take it, right? So let us try to go into the course, right? So analysis, and I'm using now, so the course title in your case, it is the Design and Analysis of Algorithms. But here, okay, you can also say that analysis and design of algorithms. You analyze and then design the algorithms, or you design the algorithms, then you analyze and try to do the modifications, whatever some tweaking you want to do, you do it, and then design an efficient algorithm for that. So a foundation course on study of algorithms. So this course is the foundation, okay, a foundation of computer science, I can say, a foundation course of the study of algorithms. Okay, it is the in fact most part of computer science and engineering is made up of algorithms. So for instance, a course on system software, okay, you have like for example, if you are studying system software, then you would see the compilers and operating systems. I think operating systems you might have already studied. I guess you already studied compilers or automata theory, right? So these there you have seen that you have designed different kind of algorithms for like parsing algorithm or the grammar check algorithm, and in this case operating in this you have learned the scheduling algorithms, right? There are different jobs and some okay, and there is a what we call the allocation policy, and all those things are covered under this operating system. And advanced courses like you have operating this one, pattern recognition, image processing, machine learning nowadays, deep learning, and all those things, all those new fields which you want to which you will be entering after your graduation. So you will be seeing that the everywhere you would be using this concept of analysis and design of algorithms, right? The whatever the basics you study here, it would be very, very useful for solving for even completing your projects in the 5th semester, 6th semester, 7th semester, as well as 8th semester, and after your graduation also, you would be, this course would be very useful. And so study of algorithms consists of analysis. Okay, the first part is the analysis. That means you would not just simply start writing the program. So you would do a lot of analysis. You would try to understand the problem. You would try to see what are the different cases, okay, how your problem should be designed, right? All those analysis will be done beforehand, and then you do the design, right? Then you design the algorithm, and then you do the profiling. So profiling is actually, it is running on the machine. Okay, you have designed the algorithm, but you want to say what is the performance of this algorithm. Then for that you need to do profiling. I think you are already aware with this word profiling, but I would also try to discuss what is profiling in the coming slides. So overall, it is the it is the study of algorithms. This is called as the algorithmics. Okay, algorithmics. And I had already told you in your introduction to programming course that if you should always say that you are an algorist, right? Algorist in the sense you design algorithms. Don't say that you are a coder. So coder does not look good, because the heart of computer science, the core of computer science is designing algorithms. So better you tell that I am an algorist, or I am the student of algorithmics, something like that you tell. But don't tell that you want to be a coder or something like that, which is which is not good for your level, right? So because you are an engineer, right? So here, what are the prerequisites for the study of algorithmics? Is the data structures, which you have already studied in your second semester, and programming in C, which you have already learned in your first semester. So these two are the foundations which are required to learn more about the algorithms. So algorithmics, let us now begin. So what is basically an algorithm? So in an abstract way, we can define that, okay, we can say that, okay, there is a system, right? What is an algorithm? An algorithm is some system, some system, and here you can see that there is an input, right? So algorithm is suppose algorithm is a known system, and you have set of inputs. And now you want to determine what are the outputs, right? You want to, the output is not known here. So this is, in such a case, it is called as the analysis. What is an analysis? Analysis is what? The algorithm is known, the input is known, as well the output is not known, the quality of the output and what kind of output you will get it, and all those the performance metrics are not known here. So this is called as the algorithm. This is called as the analysis. So okay. So you have to come up with the different. So what are the outputs? How does the system perform? What is the quality of the output? So these are some of the questions which need to be answered when you are analyzing the algorithms, right? What kind of output? What is the nature of the output? And how does the system perform? What is the quality of the output? And what is the complexity of the system to produce the output? That this is very, very important, right? So we are always focused on the complexity, the efficiency of the algorithm. So complexity of the system to produce the output. How much time does the system take to produce the output? So this is very, very important. You have already done so many experiments in the introduction to programming and a course, right? So how much time does the system take to produce the output? What are the physical requirements of the system to produce the output? So what are the physical requirements? So how many variables? What is the space? Okay, space occupied by these variables. What is the data structure that is needed to produce the output? And okay, so all those are very, very important. Okay, the physical requirements. And now, so that was the analysis, and now it is the design. So what is the meaning of design? Design means the input is known, the expected output is known, whereas the system is unknown. So this is called as the design. So now your design analysis of algorithms involves these two important concepts. I hope it is clear. In the previous slide, I tried to explain you what is the meaning of analysis. In case of analysis, input is known, system is known, output is unknown in case of analysis. In case of design, input is known, output is known, and the system is unknown. So we want to map, right? So we want to develop some algorithm which will map the given known inputs into the outputs, right? Expected output. So what should be the system that produces the desired output from the given input? So input to output, what is this? What is this system known as, right? So this is actually realizing this system involves design and synthesis problem, right? So if you want to design the system, okay, the unknown system, you want to overcome it, means you want to design it, then it is a design issue and it is a synthesis problem. So that is actually the algorithm. So algorithm is a method to solve the problem. What is an algorithm? An algorithm is a method to solve the problem. What does this mean? It means that there is an input problem and the output is the solution. And how the solution is obtained? The solution is obtained through the system. So input is fed into the system, and the system is the problem solver, or it is the algorithm. So what is the system? System is a problem solver or the algorithm. So problem given to the algorithm and you get a solution here, right? So now more technically, what you can say that algorithm is a precise method to be implemented on a machine to solve the problem. Okay, what is an algorithm? An algorithm is a precise method to be implemented on a machine to solve the given problem. So there is a problem and we need the solution. And what is this? This arrow is an algorithm, or it is a transformation function, right? We can tell it as an algorithm or it is a transformation function. So algorithm is a transfer function or transformation function, or it is a mapping function. So problem input specifications, which is here, another way of seeing this algorithm is that there are set of input instances, and there are set of output instances. So now my algorithm will be a transfer function from input space to the output space, or it is called as the mapping function, right? So here, right, so now we can see that output is almost proportional to the input, right? Output is proportional to the input, and so here output is now the function of the inputs. Okay, the output is the function of input. So here capital F is the transfer function or mapping function. The notation of F is abstract in this representation. When F is formalized and expressed as, so now when the F is formalized and expressed as sequence of unambiguous finite steps, it becomes an algorithm. So how this F will bring I to O, right? How it will bring from input, how it will transform the given input to the output space or input output, okay, how it will produce the output. So that F is a sequence of unambiguous finite steps, it becomes an algorithm. So F is treated as an algorithm. So let us take one example of a very famous example you have already studied in your introduction to programming. This is solving a quadratic equation. Okay, when you try to solve the quadratic equation, like for example here, x square minus 7x plus 12 equal to 0, right? So now your problem is to solve and given any quadratic equation. So for that, what you require? You require the value of a, value of b, and value of c, right? You require these coefficients a, b, and c. So what are the roots? What is the answer for this one? For the quadratic equation, the answer is that root x1 and x2 is the answer expected. So this is the input, this is the output which is required. So now how will we use this input to convert into the output? So let us now see that. Okay, so let us now see that. Okay, the output is x1. The output is x1, and let us have some function called f1. So f1 is a function which takes a, b, c as an input, and then produces x1 as the output. And the other output, which is x2, okay, the other function, there is some other function f2 which takes a, b, c as input, and then it produces x2 as the output. Now you know that f1 and f2. So this is what is an algorithm, right? So the capital F will be now combination of f1 and f2, which is as good as the algorithm. Now we also know that the output is dependent upon the nature of the ABC. That is very, very important, right? If you do not know the nature, then we may end up in computing wrong output. So f1 and f2 may depend upon the nature of ABC, the nature of ABC input. So now we already know that, right? So if in case of quadratic equation, this is called as the discriminant, right? This is called as the discriminant we try to calculate the value of d. So d is equals to square root of b square minus 4ac. So this here, so we now further expand, right, this algorithm. We add one more thing, that is fn. So f1, f2 is already there. This output is also dependent upon the fn, which is the nature of the roots, the nature of the ABC, right? Where fn is called, where fn is simply, it is defined as nature of ABC, which is equal to discriminant function d is equals to b square minus 4ac, right? So discriminant function d is equal to b square minus 4ac. We need to calculate this one. And now there are three cases. We already know that three different formulations for f1 and f2 exist, depending upon d equal to 0 and d is greater than 0, d is less than 0. When d is, so case d, when d is equal to 0, f1 is equal to f2 and the roots are equal, the x1 and x2 is as good as minus b by 2a, and in case of d is greater than 0, so this is in case of d is equal to 0, where in this case d is greater than 0, f1 and f2 are different, and we can see that they are so this is obtained by x1 equal to minus b plus root d divided by 2a. Similarly, x2 is equals to minus b minus square root of d divided by 2a. So this is the case when d is greater than 0. And the third case is when d is less than 0. So we get a complex roots. So f1, f2 produce complex conjugate roots. That is, x1 is equal to x plus iy, x2 is equals to x minus iy, where x is a real part minus b by 2a, and y is equal to imaginary, which is the minus, so this minus root of minus will be substituted by I, and then it becomes the, then the answer is computed here. And now the solution is now the x1 equal to 3, x2 equal to 4, and we were able to formalize that the algorithm f is dependent, that's capital F, which is algorithm, and this algorithm is dependent upon the, they're dependent upon the nature of the input as well as the roots, right, f1 and f2, because we had the domain knowledge. So we were able to solve this problem. Why? Because we know how to solve mathematically, right? So then we were able to solve this algorithmically. So now you have understood one example, means based on this example, you have known that, see, our whole idea of designing algorithm is to solve the problem, solve the existing problem, or solve the any new problem by developing new algorithms, right? By developing new. And what is an algorithm? Algorithm will be used by the computer to solve the problem. It is not me solving the problem. It is computer solving the problem. So our domain knowledge, whatever the experience we have, whatever the domain knowledge we have, will be useful in designing the algorithms and coming up with a solution. So that is the very fundamental. Now here you can now argue that, like for example, nowadays there is the trending areas like machine learning, computer vision, and all these new algorithms, the intelligent algorithms which are designed, is all based on the human experience, right? So human experience is put in designing the algorithm, and they make the decision on behalf of human beings. So that is the very important. So now whatever we have learned so far, whatever I have discussed so far, let us now formalize it in the form of an algorithm. So algorithm is the in a structured representation. So you see, please, and one more thing you should remember is that in the reports, please do not paste the code. You have to write even in the review test. You should also write. You must write the algorithms in a proper way. What is the input? So this is how the structured representation which you need to follow. You should never paste your code into your reports, right? That is, if you want to put it, you can put it as an appendix section, but not in the main content of the paper. So here is an example how to write an algorithm. So input is A, B, C, and output is X1 and X2. So what I do is that, so based on these A, B, C input provided, I can calculate what is the nature of the roots. So that is D equal to B square minus 4AC. And if D is equal to 0, then X1, X2, okay, their roots are equal. And then you can see that here minus B by 2A. This is the case 1. And case 2, else if D is greater than 0, then this is the case, right? X1 and X2 will be calculated as given here. Okay, this is the case 2. And case 3 is what? Case 3 is D is less than 0. So in this case, this is the, so now all these things are ended up within 2 flower brackets, you can see here. So this is the very structured way of representing an algorithm. So further, just to make you think, okay, can we have an algorithm to design an algorithm? So this is just a pointer for you to think, that can I design an algorithm to design an algorithm? So can we do it, right? So having understood the algorithm, is it possible to automate the transcription of a document containing an algorithm which is still written with certain amount of abstractness into the compilable source code? So given an algorithm, can you convert the given algorithm into a C programming language, or can you convert that algorithm into Java programming language? Can it convert that algorithm into a Python programming language? So that is what the can you write the code, or can you write an algorithm to do all these particular tasks? So this is the points to be think. So now let us now relook. An algorithm is the problem solving procedure which starts with the input, follows a sequence of steps, right? Sequence of steps. It is not only sequence of just steps, it is sequence of finite executable steps, right? So your steps should not be infinite, it should be finite, and it should be executable, right? And it should not, and it produces the output, and okay, and terminates. So starts with input, follows a sequence of finite executable steps, produces output, and terminates. What is the meaning of finite here? So finite means the number of steps which you define, okay, the number of steps which you define should be definite. Means, okay, clarity regarding what should be done. Definite means what, so you should be clear what is done in each and every step. It should not be an ambiguous. Okay, it should not be an ambiguous. Or finiteness simply means the statement should be unambiguous. Okay, the output should be, if your statements are unambiguous, then you will get a proper output. If they are ambiguous, then your output may not be as expected, right? So as you want, the output may not be produced. So executable means here effectiveness. Effectiveness means executability, indenting in a finite amount of resources. So this effective means executable. Effectiveness means here it should be it should not take infinite resources. It should not go into the infinite loop, right? It should end up with a so the statement should be very clear, and it should be executable. So executable in finite amount of time, finite amount of resources. And then what are the resources? The resources is that it should not take infinite time, and it should not take infinite space. That means that that means your algorithm should okay, take a decent amount of time, okay, and a decent amount of space for execution. And the 5 characteristics properties of an algorithm is that it should have an input, it should have an output, and the algorithm should terminate. It should have definiteness, okay, and it should be effective. So effective means executing on a piece of pencil and a piece of paper. This is very, very important. I think I already told you in case of introduction to programming course that the whole, okay, the whole philosophy, the whole logic here is that whatever algorithm you design, that should be executable, or that should be shown, the correctness of the algorithm can be shown by taking a pencil and a paper. Okay, the other things, execution things comes later on. What is the meaning of a coding or execution? Coding or execution means just checking whatever the algorithms you have designed, whatever the algorithms you have come up can be automated, or can be, you want to realize your dream, right? Your dream was an algorithm and now you want to realize the dream. So now you will put that your dream, that convert that into a source code, convert that into a programming code, and then you will run it. That's all. So your whole algorithm design the entire design analysis should end up, that can happen only with that should happen with just a piece of pencil and a piece of paper. That is the level you should reach, that even without running, without touching your system, without touching your laptop, you should be able to write your you complete your assignments, complete your paper, right? Complete your what you call the code or the problem which is given to you. So that height you should reach in this particular course. Okay, so now so here there are some questions, just to make you think. Like for example, see, this analysis and design of algorithms is about coming up with a solution and trying to convince yourself. That is very, very important, right? So how I have done this step, whether this is right, whether this is wrong, and whether this can be done in any other efficient way, all those questions you should come to your mind. So one such question here is that, is computing root D a definite step? Computing root D is a definite step, right? So you can just ask. So here it is yes. So it is yes. Is it an effective step? Okay, so what is the meaning of a definite? Definite means it should what I can say, that it should end up, right? It should be unambiguous. Definite means it should be unambiguous. If it is ambiguous, then computing root D is ambiguous, then you would not end up with the answer, right? So here it would end up in a wrong answer. It may give the answer, but that may be wrong. So is it an effective step? That is where the procedure should become more explicit, such as, right, effective step means it should not take infinite resource, right? It should not take an infinite resource. It should take it should end up within the decent time and space. So now that is the reason what we have done is that we have computed the root D, and then we have computed the discriminant, and then we try to separate it, the cases where D equal to 0, D is greater than 0, D is less than 0, right? And based on that, we have done the modification. This is root D is not computed. So when D equal to 0, root D is not needed at all. So this root calculation is not done at all, right? Similarly, when D is greater than 0, the root D calculation is done, it is defined, and in case of D is less than 0, right, modified as root of minus D. Okay, so even here also we'll do some simplification. We will not compute root of -1, but we will simply put that root of -1 is just an imaginary number, right? So this is how we ensure that your steps are effective. And even after this explicit formulation, is this an effective step? No, right? Because you have the case where D is less than 0, and when D is less than 0, we need to define the level of accuracy, right? The level of accuracy. See, without defining that level of accuracy, you cannot say that your algorithm is effective. So can we represent x1 equal to x plus iy and x to iy effectively? Yeah, so this is the question, right? Can we represent? So we have to define, right, to what precision this x, what precision to this complex number. Okay, so we have to define it properly. So this is some here. This is not related. Assignment questions will be given to you separately, but here just to make you think, device and data structure, symbolic representation of a complex numbers, and operations on them using newly defined data structures. So here, can you define how will you define the complex number, and how will you define operations on the complex number? All those things should be done using an algorithm. So sequence of finite steps, computing D equal to B square minus 4AC is a prerequisite to compute x1 and x2. So here, can we compute x1 and x2 concurrently? So this is the question. Okay, can we compute? So now while calculation, so now we have written algorithm. Now we are thinking some more advanced things inside the algorithm. So now, okay, can we compute x1 and x2? Yeah, we have to compute x1 and x2, but can we do it simultaneously? Yes, we can do it simultaneously because we have the parallel algorithm. So we have to think of some parallelism within the algorithm, okay, so that we because there are different cores inside the computer, inside your laptop. So that core, if it is a sequential program, then that all cores may not be utilized and the time taken will be more. So we have to use this parallel algorithm. We may need to design the algorithm in a parallel way. So then 2a can be computed concurrently with the root of d, because 2a remains the same for all. Okay, so I can calculate along with this one. So if there is a series of quadratic equations, so what type of parallelism could be useful? So this is just points to remember, and so this is what we can say, that it is a pipelining. You have already studied the concept of pipelining in case of the computer organization and architecture, right? So how different instructions are pipelined to accomplish the parallelism. So now the analysis, so factors of analysis and what kind of analysis you can do, So analysis can be, what kind of analysis, right? In the report, you have to write what is the quality of in case of quadratic equation, the quality of the roots, the accuracy in the values of the roots, overflow, underflow detection, prevention, so computation time, the space required for computation, all these are part of the analysis of an algorithm. So it is not just simply writing, solving the problem and simply writing the code. You should also do a proper analysis. So analysis in terms of what? So here in case of a quadratic equation, you can see that accuracy in the solution versus accuracy in the root D. So the accuracy of the root D defines the accuracy of the solution. So now you plot a graph for accuracy of root D and accuracy of the solution. You see another way to see the accuracy versus number of significant digits in ABC. What happens when ABC are the single digit, double digit, three digits, right? So you just check what is the accuracy of, the accuracy of the roots when number of significant digits in ABC. So one should be able to extrapolate that. So using this graph, what is your observation? So you should be able to extrapolate that number of significant digits in ABC has a bearing on computation time. So it is very natural that when the number of digits increases, for the root, not roots, for the coefficients increases, naturally the computation increases, and that should be clearly shown in the column. So now see, but now that should be done through your experiments, right? Your experiment should prove. See this is already, the answer is known to us, but now can we prove using the experiments? That is what you have to develop. Okay, so operations between, so now, yeah, definitely causes of computational pitfall is that, some of the pitfalls is that operation between one very large magnitude number and a small magnitude number, right? So this is not very it is very computationally expensive, right? In case of a multiplication, in case of a division, addition, subtraction, square root computation, right? So all these are all computational things which we try to use in our programs. And here simply just this is to simulate the computation using a hypothetical arithmetic unit capable of handling case significant digits. So this is one such question where where you can analyze, right, for handling case significant digits. So what is the bearing on of the computation, right, on the case significant digits? So how can the computation errors be reduced? Is there any alternate algorithm to solve the quadratic equation? So these are some of the questions to think on it, right? So so now, yes. So now let us see the algorithm which we designed, the solving the quadratic equation. in terms of computational resources. So an interesting note on computation time here is that, okay, now what we'll do is that we will take number of additions, number of subtraction, number of multiplication, division, square root, and some special computation. So these are the operations which are involved. Now, when in case of quadratic equation, when d equal to 0, what is the case? Okay, so when d equal to 0, you can see that square root is avoided, right? The square root is not calculated, but there are some multiplications and divisions which are 3 plus 3, and number of addition subtraction is 1. So here you can see that number of assignment is the 1 plus 2. So total number of operations which you can see that when d equal to 0 is 11. Okay, when d is greater than 0, the number of operations is 19. When d is less than 0, the number of operations is. So now you can see that the efficiency of the algorithm. Now here only you can observe what is the best case, what is the worst case of this algorithm. What is the best case of this algorithm? The algorithm will be in the best case when d equal to 0 and number of computations which will be performed, number of operations which will be performed will be 11, and the number of the worst case would be that when d is less than 0, there okay, the roots are complex and the computation time taken is 20. So least number of computation is 11 and most number of computation is the 20. Say this is so. In other words, there exists C1 and C2 such that C1 is there. So this says that the computation time varies based on the condition and the nature of the input. That's what we can remember here. And now one more very simple example is to this. Already you know that you already done experiment, means assignment based on that one, swapping of the numbers using a what we call the additional variable. Here in this case that is the temporary variable, but here in this case we are not using any temporary variable but doing some operations, doing some arithmetic here and then getting the number swapped. So the problem is here exchanging or swapping the contents. So here I am reading A, B, C, then I am taking T as A as B, B as T. So this is the swapping algorithm. The other version of swapping is that you simply take two numbers here, okay, and then you do A plus B, and then you B equal to A minus B, then A equal to A. So this is without using the temporary variable. So prove both the algorithms would work, which would suffer from more computational pitfalls. So now you have already understood that, okay, there are some advantages and disadvantages with both the algorithms. So let us now see number of assignments. So this is version 1, version 2. This is algorithm. Now number of assignments here is the 3. Number of arithmetic operations is 0 here, and number of variables used is 3 here. In this case, what happens? Where there are no, I think here there is here there is no temporary number of variables is just 2, right? Number of variables is just 2, and number of arithmetic operations is 3, and number of assignment is 3 here. So an example of a space and time trade-off. So now you can see that, okay, this is this involves you can see that this is okay. So these are the some of the time and space trade-off. So this some would require more number of variables and some would require more time, right? So that is how the space and time trade-off in this particular example. So another example, so another best example is that now let us assume that the multiplication operator, that is star, is not available in your programming language. So in your programming language, this is let us assume that the multiplication operator star is not available. Now I tell you, can you multiply two integers? Okay, compute the product of two integers m and n without using the star operator. So algorithm is star is in terms of what is the algorithm now? So instead of star, to realize star, what I would do is that I would try to do the repeated addition operation. What is multiplication? Multiplication in terms of addition is the repeated addition. So suppose you want to multiply 2 into 3. So 2 3s are 6, right? So 2 into 3 will be, answer will be 6. If you add 2 3 times, again you will get the answer as same 6. So this algorithm can be written in two forms. Version 1, version 2, right? So what I would do is that now there are two integers m and n. So version 1 would be that what I would do, I would take a for loop and then I would move that for loop because m and n, I would move from for I equal to 1 to m. Simply I would add n, right? I would add n, okay, m times. I would add n m times, right? So p is equal to p plus n will be added, n will be added m times. Here m will be added n times. Here m will be added n times. So this is version 1, version 2. Now just think here, which is more efficient algorithm, whether version 1, version 2, which is the most efficient algorithm. So now for that we need actual input. So let us now give some value to m and n and let us check which is going to work. So let us take now the value as m equal to 12 and n equal to 6. Okay. Now let us try to compute with version 1. So version 1, what it will do, it will add, right? It will add n, that means this, it will add n, that is 6. How many times? 12 times. So this is 12 times. So this is 12. Whereas in case of version 2, it will add m, how many times? 6 times. So which one is more efficient? Now you just see this graph here, right? You see this graph here. So version 1 will take this much time. Version 2 will be, so the loop will be running 12 times in this case of version 1. In this case, the loop will be running 6 times. So now what is this? So this is the saving. What is the saving in time? You can see here, this is the saving in time. So now, can you modify this? Now version 1, version 2, you have understood. So now can you try to do some kind of pre-processing or some kind of intelligence? Can you put inside this algorithm such a way that whatever may be the m and n value, you will get the same. You will get the efficient time, means you will get the what you call, you will get the means the efficient execution of the program will takes place, right? So now this is possible. I think later on we'll see that one, that this is possible. How? Let us try to add one simple statement called, if m is greater than n, then you swap m and n values, right? If m is greater than n, you execute it this way. If m is less than n, then you execute it the second way, something like that. So something like that you try to do it, right? So here, so in that case, both will be useful, right? Both the this version will be available, but it will be pre-processed depending upon the m and n values. So now let us perform a detailed analysis to estimate the computing time. Okay. So now this is very, very important. You have already done it in case of introduction to programming course. And here also I would just try to explain for the sake of completion here. So what is this? So let us perform a detailed analysis to estimate the computing time. And this is what is called as the a priori analysis. So a priori analysis is calculating the time complexity of the algorithm without touching the machine. With only pencil and paper, you should be able to. So this kind of analysis is called the a priori analysis. Analysis before executing the algorithm on the machine. Testing an algorithm practically by executing the code on the machine is called the a posteriori analysis. So a priori analysis is without execution. A posteriori analysis is with execution, right? So you're both the a priori analysis and a posteriori analysis should match finally. Otherwise, there is something wrong in your algorithm. So this is called as the profiling. So profiling is a process of executing a correct program on the data sets and measuring the time and space it takes to compute the results. Okay. So profiling is also necessary to study the performance in the quality of the results computed, and the profiling process helps to fix up the reasons for the deviation, understand the scopes of improvement, and motivates one to think in terms of alternate design or redesign to realize optimization. So now you have understood that profiling will help you in getting the idea of time and space, and also you would understand the quality of the output, and this would also help you that in understanding whether there is a deviation there is a deviation in the answer from the actual output, right? So it would also suggest you that okay, it is taking more time or it is taking less time, something like that, right? Scope for improvement also is possible with this profiling, and also it will give the it will help you in redesigning the algorithms to realize the optimization. So now overall you can see that analysis is theoretical, practical, right? So theoretical analysis is a priori analysis, and a practical analysis is the a posteriori analysis, and this is called the profiling. So analysis, a priori analysis, and this is after the execution of the program is called the profiling. And for the assessment of computing resources, we have time and we have space and we have computational performance. And that in the case of computational performance, as I explained earlier, that accuracy, right? I told accuracy. So what is the quality in the computed result? The quality of the computed result is the computational performance. So this is the overall view of design and analysis of algorithms. So when you design in any algorithm, analyze in any algorithm, right? When you develop in any algorithm, these are the things which you should focus: analysis, a priori analysis, a posteriori analysis, profiling, and computing resources. So without this, your algorithm remains incomplete. Okay, without this, your algorithm remains incomplete. You must do time complexity analysis, space complexity analysis, and also you must check the quality of the computed results, whether you are getting the okay. So there is another keyword called as validation. So validation is checking whether your algorithm is producing output, okay, right output for the right input, right output for the right input. So this is called the validation. So testing and validation. So these things you will learn in your higher, when you take the electives like image and video processing, computer vision, you will learn more performance metrics there. But right now this is sufficient for you. Or when you try to solve some applications, this your computational performance will be in terms of different aspects. Okay, different aspects. So now let us now see how to do a priori analysis. So this already has been explained to you, but still I would try to do this one. Okay, how to do theoretical a priori analysis. Okay, we shall follow the notation of unit time. So now we know that, right? So now some of you might write this program in your laptop, or some of you may write in a program on the desktop, or some may write in the high performance computer, supercomputer, somewhere. So what we do is that, so the time from the different machines would vary. So just for the sake of what we call the simplicity, what we would suggest that in the theoretical analysis, that is the a priori analysis, we would just make an assumption that the operations take 1 unit of time, right? We define that every operation takes 1 unit of time. After that, what we would do is that we would count the number of operations, and then we would multiply with the computing power of that particular machine, and that would give the actual running time of this your algorithm on that particular machine. So for simplicity, what we would do is that, okay, we would assume that the operation time consumes unit time for any operation. Though you in your computer organization and architecture, you have already studied that addition, subtraction, multiplication, division, they do not take same number of cycles. They take different number of cycles for execution. But for the simplicity, we would assume that there is one. We would treat as 1 unit of operation for. So all arithmetic operations, plus, minus, subtraction, division, mod, is 1 unit of time. Comparison, all these are 1 unit of time. Logical operations, NOT or XOR, you can take 1 unit of time. Assignment operator, also 1 unit of time. So now what you would do is that we try to calculate number of operations and the frequency of operations. That is the key here. Number of operations in a particular instruction, and what is the frequency of operations, because frequency is the key here, right? So now let us take the same example of multiplication. Okay, so now in case of the multiplication algorithm, we try to initialize, that is p equal to 0, right? P equal to 0, and for I equal to 1 to n, right? 1 to n, I added m, right? I want to add m n times. So this is as good as multiplying m and n, right? To get the value of m and n without using the multiplication operator. That was the program here. So now let us try to analyze this one. Okay, let us take now one by one. Assignment operator, P equal to 0, first instruction. So this operation is here is assignment operator, and the time taken is 1 unit of time. What is the frequency? The frequency is 1, because this will be executed in the program only one time. If I run the program once, it will run only one time. What happens for I equal to 1 to n? For I equal to 1 to n, right? In the for loop, what would happen is that, okay, for in the for loop, let us take the for I equal to 1. Okay, in this, let us take that if you write a for loop in C, right? So for it will be for I equal to 0, I is less than n, I plus plus. For I equal to 0, I is less than n, I plus plus. So now if you take in that case, if you take for I equal to 0, I is less than 1. So I equal to 0 will take 1 unit of time. I is less than n, it will take another unit of time. And I plus plus is I equal to I plus 1. So I equal to I plus 1, there is a 2 unit of time. So total for loop means total operations inside the for loop in case of a C programming language is 4, right? It is the 4. So here in this particular example, we have taken only for here we have taken only I equal to I plus 1. We have taken I equal to I plus 1, only increment, that is 2, and I is greater than n. So here we are checking only 3 conditions. But whereas in case of C language, whereas in case of C language, the for loop takes 4 there are 4 operations, but here it is only 3 operations. Okay, so here it is equal to, plus, and greater than. So that is why it is written as 3. And what is the frequency? How many times this for loop will be executed? That is the key. How many times it will be executed? This will be executed n times for true case and 1 time additional for false case. Okay, so this I suppose this is 5. I equal to 1 to 5. So 1 to 5 is it will run I equal to 1, I equal to 2, I equal to 3, I equal to 4, I equal to 5 also it will run. Then I will get incremented, I equal to I plus 1. Then I will become 6. Again, then this for loop will come here 6, whether 6 is less than, whether 6 is greater than n, or means the 6 is greater than, yes, 6 is greater than n. So condition would fall. So the running time would be n plus 1. Already you know this one, right? N plus 1 here. And what about the inner loop? What about the inner content? Here you can see that there are 2 operations equal to and plus, and then what is the frequency of this? Frequency of this is n, right? Because the outer loop runs n plus 1. 1 is the false case, but all the true case it will learn the means the inside one will run. So this is the n. Okay. So this is the n. So now simply now is only arithmetic. Multiply the number of the operations and the frequency of the operation. And now you can see that 1 into 1, 3 into n plus 1, 2 into n. And now you can see that the running time is proportional to 5n plus 4. So you please understand 5n plus 4. If n is large, then okay, if n is large, then what you can say that 5n will be simply it will be n, right? T is proportional to n. And now we introduce the big O notation. Big O notation is the worst case analysis. The worst case complexity of this particular algorithm is the n. What is the meaning of n? N is the linear. So what is n? 5n plus 4. What is the, if you draw the graph of 5n plus 4, it is just a linear equation. You will get a linear. So the running time of this algorithm is linear. That's what it says. So total computing time is bound by T is proportional to 5n plus 4, and this function obtained by strict sense analysis gives the actual computing time function. In this case, it is a polynomial function. In particular, it is a linear function. So here 5n plus 4, you can see that 5n plus 4, if you this is not 5n plus 4, this is actually, you can tell this is cn, that means this passes through the origin. I have left this 4 here. So now here you can see that t is okay, t is less than, where c is a constant dependent on the machine. So you can say that t is less than Cn. So if you try to substitute this with some constant c, and the time will always be less than Cn. That is why we say that worst case, no, that big O. Big O, when we write, that means that whatever that is the worst case time, and whatever the time of the algorithm will be lesser than that. So that is why we say that t is less than or equal to Cn. So actual computing time is bound by Cn, and computing time does not exceed Cn. So this is the maximum computing time of the algorithm, and your algorithm, you can see here, your computing time will be here. Okay, the computing time of the algorithm will be within that, because this is the worst case. This is O of n. Okay, this is O of n. Okay, your algorithm will be. Now this is okay. This is a very general way, but if you still want to define it in this case, like for example, this is phi n plus 4, right? This is phi n plus 4. The 4 is the intercept. Now you can see that this line will be just shifted, right? Sorry, I am unable to draw the straight line here. So this would be a straight line, okay? And your computing time would be, you can see here, your computing time would be this one, right? So your computing time would be, the worst case time would be that this one. So these are some of the things which you should remember, okay, in this case. And now, okay, so the another thing is that when two strings are compared, the computational time is dependent upon the length of the string, as the string comparison involve bit comparisons and shift operation. So does the nature of the computing time depend upon the number of lines in the algorithm code? I think till now you are already in the 4th semester, so you should have already understood. Does the nature of the computing time depend upon the number of lines written in the algorithm or code length? No, right? It is no. It is not dependent upon the number of lines you write in your code. Does it depend upon the number of operations? Okay. Yeah. Okay. Does it, just think. Does it depend upon the machine? Just think. Does it depend upon the size of the input plus output? Okay. You think. The nature of the computing time depends upon the size of the input and the output, most often upon the size of the input, right? This is the fundamental thing. So now when we define the complexity of the algorithm, we always define the complexity of the algorithm in terms of size of the input, right? Size of the input. So now the other way of computing, so we saw now how to calculate the time, that is a priori analysis. Now how to do a posteriori analysis, right? How to do a posteriori analysis, that is measuring the computing time practically, that is profiling. How to do profiling? So system clock using time. The first simple way is that which you already done in introduction to programming course, that you take a system clock, right? You start the clock start and clock end, and then try to calculate. So system clock you can use which is provided by the programming languages. You can use for the type of so you can just use it. And now if you want to make the profiling irrespective of the machine, where you are running, so in that case what you do is that you introduce a counter called time equal to 0, right? Introduce a counter as shown below, like time equal to 0. Then simply after the execution of this statement, you simply keep on adding number of operations to the time. So now here time is 0, p equal to 0 here, time equal to time plus 1. Now here for I equal to 1, okay, for I equal to 1 to n do, in this case there are 3 operations. So time equal to time plus 3, and after this execution of this particular statement, time becomes time plus 2. So now you run this program, practically you run this code, right? You run this code and then just print the value of time, calculate the value of total time. So total time multiplied by the computing power of the machine will give you the actual running time of your machine. So this is what is another way of doing the profile. So all those things should be done in the assignments, whatever you do it. Okay, here. So improved version of the algorithm, yeah, that's what I had already suggested. So now how can we improve this algorithm of performing m into n, okay, without using a star operator? So then simply what you do is that you try to compare right? If m is greater than n, then index becomes n, element becomes m. Else index becomes m, element becomes n, and then you put one for loop for computation depending upon the index as well as the element. So based on this index, right, how many times you want to, because we want to reduce the number of iterations, n value we want to reduce that index. So that's how we try to make an intelligent decision, that we would set the index to the smaller one, right? We would set the index to the smaller one, and now this program runs for the smaller index. That is the key here. So now let us take the what we call, let me take the number of operations for this new program, which we algorithm which we have developed here. You can see that the time is 0 here. Okay, m is greater than n here. The time is you can see here the 3 operations. Here it is 3, and here p equal to p plus element. Here it is 3, and now the number of times you can see here, right? All those things. This already you okay. So now index plus 1. Just now multiply this. 1 into 1, 3 into 1, 3 into index plus 1, 2 into index. So all those index is here. There we have taken n values, right? So here we have taking the index. So now you can see that this is almost, now when you try to calculate this one, right? When you simplify this one, then t is proportional to index. So t is almost proportional to the index. So what is index here now? In this case, index is the minimum value m and n. Please remember, what is index? Index is the minimum of m and n, right? So this here the algorithm, for this algorithm, the minimum value will be the complexity, right? Complexity of the algorithm. So an algorithm with linear computing time, definitely either it is m or n, both are linear. So in short, it is a linear algorithm. So that's how you can. So I would stop it here. So in the next lecture, I would try to give you some algorithms. Okay, some more advanced algorithms we will discuss.